Hey guys, so in the next video, we're going to be looking at simple harmonic motion from a different perspective, right? In the first video, we looked at a graph that had energy versus position. In the next one, we looked at position versus time, velocity versus time, acceleration versus time, right? This graph now looks at acceleration versus displacement or position. Okay, now this is going to be a little bit different. We like to think about things happening in this direction being time progressing, right? And we like to see as something moves, we like to see that object moving as time progresses, but that's not what's going to happen here, right? This one only goes to a certain position because when we have something that's oscillating, whether it be going back and forth or up and down or anything like that, there is a limit to how far it oscillates before it turns around and it goes back the direction that it came. So that's exactly what's happening in this graph. Your object is moving this way, it's going to stop, and it's going to come back the other direction. The further you get away, the greater the force, the acceleration is back in the opposite direction, which is why we have a negative slope. So that's exactly what we're going to be looking at here in this question. So this shows an object's acceleration with respect to its position. The first thing that it asks us to do is find the amplitude of the oscillation. Now that's pretty easy, that's pretty straightforward because we know that the center of the oscillation is at x equals 0. So this is the center. So from there, it's going to go over to the right and then it's going to go over to the left. Now I'm looking at this and seeing that maybe my graph printed a little bit weird. This should be a -1, this is 0, that would, this would be a +1. This would be -1, -2, -3, -4, -5. You know what, I'm just going to do that over again. All right, guys, so in our next example here, we're going to be looking at acceleration versus position or displacement. Now, this is going to be a little different from the last ones. We've looked at energy versus position. We've looked at position versus time, velocity versus time, acceleration versus time. This one is acceleration. Now remember that the acceleration and the position for simple harmonic motion are directly proportional to each other. They have direct variation or directly proportional. Now what that means is that it's a straight line that goes through 0, 0, and that's what we see here. The 0, 0 is very important because when our position is 0, when we're at equilibrium, there should be no force. There should be no acceleration. The forces should be balanced, right? And so therefore there's no restoring force. Now it's important to also to know that when there's a pendulum, the pendulum is always in circular, it has that circular motion there. And so there is a net force, but it's not a restoring force. It's not pulling it back to that equilibrium point when it's at the bottom of its curve. All right, so this is going to be acceleration versus displacement. Now the first question is actually pretty straightforward, right? The first question asks us to find the amplitude of the oscillation. So we just look at the graph. The graph shows position. And so therefore, we know that the object at some point is going to be at 0. That's its point of equilibrium. And then it's going to go over to the right. And I can see right here at the right that it goes over to 5 times 10 to the -2 meters, so 5 centimeters. And then it goes back to the left. And then over here it goes to the left until it gets to -5. That's how simple harmonic motion works. It goes one direction and then it has the same amplitude back in the other direction. So the amplitude, remember, is the distance from the center to the maximum displacement, which in this case would be 5 centimeters or 5 times 10 to the -2 meters. So that first question, pretty straightforward, 5 centimeters or 0.50 meters. Silly me. Not this, but 0.050 meters. Sorry, I got to make sure it is centimeters, but it is. I'm still going to add that second digit for. So thank you. If you were saying, Bishop, I want to stop, you made a mistake. I hope you were doing that at home. And if you were absolutely correct. It should be 0.05, and that's all right. Okay. Secondly, it wants us to determine the period. And so when I want to determine the period, I should be looking through my equations. I should be trying to think about what equations have period. Now I've got three that come to mind right away. I have the period equals 1 over the frequency, which is 2 pi over omega. Okay, that one. I've got the period equals 2 pi times the square root of m over k, but that's only for oscillating springs. And then I've got the period equals 2 pi times the square root of L over G, but that one is only for pendulums. And so therefore, I'm going to go with the one that is period equals 2 pi over omega. Now I chose this one. It's also equal to 1 over frequency, but I chose this one because my graph has acceleration and position. And I know that there's a second equation that connects acceleration, position, and the omega. That's the first equation in our formula packet, which is that A is equal to negative omega squared x, right? And so that then, I'm looking for the first thing I'm looking for is an equation that has period in it. But once I have that, I need to be able to connect that to something that I can actually get information for. So keep that in mind, is that sometimes the first equation won't have everything in it, and you may need to use the second equation to then make that connection. So if you want, you can algebraically solve for omega and you can plug that in, but here it's simple enough just to solve for omega. So I can pick any point on the graph. It's usually best to pick a point that is as far away from the center as possible. That will decrease our uncertainty, especially the percentage. So I'm going to choose this point over here. That is 5 for x, and then negative 6 meters per second squared for the y value, for acceleration. So I'm going to go negative 6 equals negative omega squared times x, and x is 5, but that is 5 times 10 to the negative 2. So I'm going to put 0.05, all right, just like that. That then means that I can solve for omega. So I'm going to take the negative 6, and I'm going to divide it by a negative, so that will leave me with a 6. Then I will divide by the 0.05, which gives me 120. So that means that omega squared is equal to 120. Then I will take the square root of that 120, and I get that omega is equal to 10.95. Now this should be in radians per second. That's the units of omega, the angular frequency or the angular velocity. So that will be radians per second here. All right, now I can take that and I can put it into the other equation and I can solve for t. And so now the 10.95 goes right there, and I'll just say period equals 2 pi over 10.95. So it is important that you're using the correct units here. I made sure that I put it in meters. If I put it in meters, then I'm using SI, and so I know my units are radians per second. And so in the end, I'm going to go 2 times pi, and then I'm going to divide by the 10.95. And my final answer is that the period is equal to 0.5735, but I do know, actually I'm going to go ahead and put a 0 in front. I know that's helpful sometimes for you at home because it might be hard to see the decimal. So 0.57 seconds, the units should be in SI units, and so therefore 0.57 seconds. All right, there you go, no problem. Hopefully, this being the second time you've seen a problem like this, it wasn't too bad and you were able to figure it out. See you next time.